Giant covalent structures for Cambridge iGCSE Chemistry. Cambridge iGCSE requires an understanding of the properties of giant covalent structures, and then three particular examples: silicon dioxide or silicon 4-oxide, diamond, and graphite. Some covalently bonded solids have very high melting points. Let's just review the structural types we will meet with covalent bonding. We can have simple molecules. The melting point is low. You may or may not have met polymers. Well, they also have low melting points. However, if we have a giant covalent structure, the melting points are very high. Two typical substances with giant covalent structures in the syllabus are diamond and silicon 4-oxide, and we will look at their properties. However, graphite has atypical properties. That is, it shows properties that other giant covalent structures do not show. The first substance we'll look at is silicon 4-oxide. The chemical formula of silicon 4-oxide is SiO2. Silicon is a nonmetal, oxygen is a nonmetal. So we would expect the bonding to be covalent, and indeed it is. However, if silica is heated strongly, the solid will not melt. You may have done this in the laboratory. That means the structure of silica, silicon 4-oxide, cannot be simple molecular or polymer. Both those structures produce low melting points, but silica has a high melting point. So the high melting point of silica indicates a giant structure. Each silicon has 4 outer shell electrons and therefore forms 4 covalent bonds. Here's a silicon, 1, 2, 3, 4 bonds to 4 oxygens. Each oxygen forms 2 covalent bonds. So here's our oxygen, 1 covalent bond, 2 covalent bond. So we'll see the ratio is 1 silicon to 2 oxygens, 4 bonds to 2 bonds. This structure, of course, goes on until we run out of atoms. It is a giant structure. To melt, that is to separate these particles from in the solid state to form a liquid where they've got some freedom of movement, you're going to have to break the strong covalent bonds between silicon and oxygen. This requires a lot of energy. Therefore, the melting point is high. Moving on to 2 forms of carbon which we need to compare, diamond and graphite. Carbon forms 2 types of high melting point solid at room temperature, diamond and graphite. You are expected to recognize this structure as being diamond. We've got a central carbon with 4 carbons covalently bonded to it, 2 coming forward, 1 above and 1 going back into the picture. So it's called a tetrahedral arrangement. You are expected to recognize this structure as being of graphite. So we have carbon atoms, and we will go through it in more detail in a future slide, in layers. Both of these are giant covalent structures. Diamond shows typical properties, graphite has some atypical properties. So let's take one of these forms first, diamond. Each carbon in the diamond structure forms 4 strong covalent bonds. So we have a central carbon forming 4 carbon-carbon bonds. Of course, this carbon here will form another 3, so it's going to extend to form a giant structure which carries on and on and on until we run out of carbon atoms. Each carbon in the structure held in place by 4 strong covalent bonds. So what would we predict for the properties? Well, if the particles are held, the atoms are held by strong covalent bonds, it's going to be a lot of energy needed to break them. The melting point will be high. To move these particles around, you're going to have to hit them with a great deal of force. Diamond is very, very hard. None of these particles are mobile, they're fixed in position. None of these particles carry charge. Diamond is a non-conductor. And these properties are the same as we would expect for silicon dioxide. So graphite, in contrast to diamond, has an arrangement with carbon atoms in layers. You'll notice that the carbon atoms form within the layer hexagons. I'm tracing one out with my pointer. So we've got parallel layers of carbon atom hexagons. That is, if we look at the highlighted carbon here, it's only bonded to 3 other carbons. That means for every carbon atom, there is one outer shell electron that is not involved in bonding. So every carbon atom has an unbonded electron. Those electrons are free to move throughout the structure. That is, they are delocalized. You'll also notice the distance between the layers is quite large, so there are no covalent bonds between the layers, just weak intermolecular forces. So the properties of graphite are not typical of giant covalent structures. There is a high melting point, which is typical, but other properties, such as being soft and slippery, are certainly not. We can explain that by realizing that these layers can move over each other easily. So it's rather like our explanation of the properties of metals. The layers of carbon atoms can slide over each other easily. There is only weak intermolecular forces between the layers. Another exceptional property of graphite is it is an electrical conductor. These electrons, as we highlighted earlier, are delocalized and free to move throughout the structure and carry charge. Here are a couple of review problems about diamond and graphite. Which of the models A and B represents diamond and which graphite? You can speak it out as if you're talking to me or write it down. Okay, so diamond on the left, a model of graphite on the right. Second question, which substance has the following use as a lubricant? Which of those, diamond or graphite, could be used as a lubricant? Which could be used as an electrode, perhaps in the school laboratory? Which of diamond and graphite, A and B, could be used as an industrial cutting tool? Think about it, choose diamond or graphite in each case, come back to check your answers when you are ready. Okay, so as a lubricant, it's going to be graphite. Machine parts are coated with graphite because Graphite forms a slippery surface. Graphite is also an electrical conductor, an inert electrical conductor, a very useful property. So used as an electrode, graphite. Diamond is exceptionally hard, so it's used as an industrial cutting tool. So well done for finishing. If you want more practice, which I would advise, use your textbook questions first, then find past paper questions. If you haven't come across Physics and Maths Tutor website, I would recommend it. Nothing to do with me, it's just got loads and loads of past papers. For more related chemistry classes, look at the playlist or the links in this video description. If you found this class helpful, please recommend it to a friend. Subscribe for new classes and last-minute exam tips. Please like.